And good afternoon, everyone. Now I can erase the roll and sign. So I apologize already to you by email. And let me do it again orally. It's really embarrassing, but it happens every now and then. What's most important that we can straighten it out in time. And let me begin by writing some details concerning these hereditary subsets. Indeed, it is not only it's nice topology, it's the Alexandrov topology which we are after. So let's review it. I assume that Hi, with I running some arbitrary index set I, is, as I said, is an arbitrary family of hereditary subsets. And graph is arbitrary. Oops. Then both the intersection set and the union set are hereditary. And basically we know why, but I want to write it formally. It's exactly the same reasoning that we did before. That's where you get your idea from. But it's good to write it formally and note that it is really working for an arbitrary family. No finiteness is needed, neither for the intersection nor for the union. That's why it's the Alexandrov topology, because we have arbitrary intersections of open sets open. Okay, why? Why is the case? Let's have a look again really quickly. So suppose otherwise. I mean, suppose that the union is not hereditary. So suppose there is a vertex in the union emitting an edge let's call it E, such that the end of this edge, T of E, is not in the union set. Okay, but what does it mean? Well, so if I have a vertex V in the union set, then there exists an index J such that this V is in a given Hj. Okay, so then there exists J in I such that V is in Hj, and if T of E is not in the union set, it's not in any of the components of the union set, right? So it's also not in Hj. So Hj is not hereditary. And we get the desired contradiction, right? So by assuming that the union set is not hereditary, we prove that at least one of the components of the union set is not hereditary. So when you reverse the implication, if all of the components of the union set are hereditary, then the union set is hereditary. Okay, and much in the same way we argue for the intersection. So much in the same way. Suppose there is a vertex V in the intersection. And such that, okay, emitting, of course, emitting an edge emitting an edge E which ends outside of the intersection. But now sort of you look first at the second part of the phrase. So then, because TE is not in the intersection, then there must exist an index J such that T of E is not in Hj, okay? So then there exists a J in I such that TE is not in Nj. And well, if it belongs to the intersection of all HIs, in particular, it must belong to Hj. And V belongs to Hj. So again, we can conclude that Hj is not hereditary. And this gives us the desired contradiction, so that we know that an arbitrary intersection of hereditary subsets is a hereditary subset. All right. So this is very simple reasoning if you are not at the blackboard trying to resolve it. But we did resolve it just from the picture. So that's exactly the same idea. But this time, this picture can be formalized for an arbitrary family. I think later on we have some statement about, no, there is no statement about finite families, but it might happen that some things hold true just for finite intersections and not for arbitrary intersections. Here it's good for arbitrary intersections. Okay, so now combining this with the fact that both the empty set and E0 are hereditary, we infer that the set of all hereditary subsets is an Alexandrov topology on the set of all vertices E naught. Okay. Good. So this, all these considerations lead us to the following proposition, which is very nice, elementary, but nice. Well, in a way, we didn't have to do this reasoning. It follows from what I'm about to write, but I think it's nice to see it directly in terms of graphs without just going to a more general case of playing around with upper sets in the Alexandrov topology. But of course, we have this reasoning done in bigger generality. But how do we relate it? That's the key thing. How do we relate a preorder to such collection of open sets? I was explaining it during recitation class some time ago. So I'm going now to do it very briefly. The most important thing is the shear statement, okay? So let E be a graph. I write this, magic phrase, let E be a graph, just to make sure that it's clear that I don't assume anything whatsoever about the graph E, all right? So the set of all vertices is preordered by the following relation. We say that a vertex V is less or equal to a vertex W. By definition, if only if there exists a finite path such that D is the beginning of this finite path and W is the end of this finite path. Okay. Moreover, because this is a trivial statement, it's just good to have it highlighted, the set of all hereditary subsets of E naught is precisely the Alexandrov topology associated with or to our preorder. Okay. Oops, I wrote in my notes partial order and it should be a preorder. I see a typo which I have to correct. Okay, this is elementary, so proof is very immediate. So for starters, note that, that this defines a preorder. I'll not even write it down. This is completely obvious because a preorder has only two properties. It must be reflexive and transitive. Obviously, V is equal to W, then the finite path of length 0, namely V equal to W, is exactly what satisfies these two conditions. So V is less or equal than V. Now, if I have a path from V to W and I have a path from W to Z, then of course, by concatenation, I have a path from V to Z. So obviously it's transitive. Let me not even write it down. So this is more like a definition than a claim. But what is important, so maybe I should get it out of a proposition and keep it this on as a proposition. Because although actually this is also elementary, but at least I have to recall the Alexandrov topology, okay? So recall that a set U is open in the Alexandrov topology of a preorder. Now let me use curly less or equal to. By definition, if and only if, you have the following implication: X in U and X curly less or equal than Y implies that Y is also in U. So these are called upper sets because if you have any element in your upper set, then anything bigger than this element is also in this upper set, hence the name upper. Okay, so that's exactly the definition of the Alexandrov topology related to the preorder. And you see, because we know that this is a topology, this is just part of I don't know, the theory of preorders, if you want, that reasoning is redundant because it's a special case of more general reasoning. So now we can just conclude by noting that for this curly partial order taken to be not partial order, sorry, preorder, because we don't have anti-symmetry. See, when we allow loops, we cannot say that if V is less than or equal than W and W is less than or equal than V, we cannot say that V is equal to W because we might have a path which is a loop. So it's just a preorder, not partial order. But now if we take this general preorder to be our preorder in the set of all vertices E0 with a preordering structure given by finite paths, then note that this definition of an upper set is exactly the definition of a hereditary subset in terms of in this finite path version. Okay. So how to write down? This is precisely the finite path version of definition of a hereditary subset. Okay, which ends the proof. So in other words, right, because what does it mean? If x is less or equal to y, well, then I have these two vertices and there is a path in between them, okay? And hereditary property requires that the endpoint of any path starting in my subset must also end in this subset. So that's exactly the requirement, okay? So the definitions just coincide on the nose. So the claim is obviously true. And I think we are done with hereditary subsets. Now we can pass to saturated subsets. So I think I cleaned up the mess which I created later on. But on the other hand, I must say that of course, maybe I wasn't looking hard enough, but I've never seen anybody writing about the set of all hereditary subsets as a topology. I've never seen it. It just escaped me. And but of course, Shao was right. This is an obvious observation. Everything I'm doing here is completely elementary, and it should be basically in every textbook. Okay, so now let's go back to saturated subsets. I'll give you a definition, but before I proceed, I need to clean some air. Namely, I need some definitions which I should have given you some time ago, but I didn't. Now they are somewhere at the beginning of a lecture notes, but I have to write them down. I mean, I was mentioning this stuff in my introductory lectures, overview lectures about the whole course, but now let's write them down formally. So first thing, I mean, this is just terminology. There's nothing deep. I'm not creating some concepts. I'm just giving names so that it's easier to speak about certain things. Okay. So first definition, a vertex V is called regular if and only if it is not a sink. So it is an emitter, it emits at least one edge, but it is a finite emitter. So when I take the number of elements in the preimage set under S applied to V, then it's finite. Of course, I could just keep writing sink and write here 0, strictly less than this number, whatever way, okay? So this is very important because it happens all the time, but you have to pay special attention to regular vertices because you see regular vertices are exactly vertices at which you have a Kunstkrieger relation. And I believe, let me look it up. When I was, of course, we didn't get to Kunstkrieger relations yet. Yeah, this is where you use the regularity property, okay? And there is another important definition. It's also used extensively, namely a graph is called rho finite whenever each of its vertices either a regular vertex or a sink. So in other words, there are no infinite emitters, okay? And you can guess why such graphs, I mean, where you have this strange name rho finite from? Well, just from the adjacency matrix, okay? When you write the adjacency matrix of a row finite graph, well, the matrix will be row finite, I believe. So whence the name. But what you should remember is that we are talking about the situation in which we don't have infinite emitters, okay? So in particular, any graph with finitely many edges is always row finite. And this is, okay, on one hand side, it's just a terminology, but this is important terminology. Why regularity is important, I just explained. But row finiteness is also very important because in many theorems, you really have a shortcut if you assume that your graph is row finite, which when you combine with the fact that really very, very many important examples in non-cumulative topology are row finite, not all of them. Typically, when you go to fixed point C-star subalgebras, like Podley spheres and projective spaces, they are no longer row finite. But when you look at many, many other graphs, this row finiteness is satisfied, okay? So that's a good assumption because it simplifies many, many reasonings, simplifies proofs. And well, certain statements, I guess, are valid only for row finite graphs. And still we have plenty of interesting cases where that assumption is satisfied. Because if you assume that you have a finite graph, well, then you have a finite C-star algebra, so this is just a bunch of matrices. It's not very interesting from the point of view of functional analysis. But when you have something that is row finite, well, it still can be quite interesting. And the combinatorics of the graph is very elementary. Okay, and I will just need this terminology. This is why I wrote it down here. Now it's at the beginning of the lecture notes, but I needed to speak about saturation property, just will be handy. So you see, now with this definition, I can reformulate the definition of a saturated subset, right? I can write H is saturated if and only if there does not exist a regular vertex V outside of H, and such that when you take all edges emitted at V, they all end in H. Okay? So regularity is already needed to define what saturation properties. All right. Okay. So this is where we stopped a week ago. So now we continue. I defined the saturation property, well, in a pretty standard way. But now let me write it really formally, let E, because this was just a reformulation. Now this is a concept I'm introducing, that E be a graph. I emphasize it just to make sure that you know that I mean an arbitrary graph. And H is just any subset of a set of all vertices, okay? So the intersection of all saturated subsets containing H is called the saturation of H, and we denote it by writing a bar over H, and it's denoted by H bar. So see, it's not a coincidence because it's exactly how you define the closure of a set. You take the intersection of all closed subsets that contain a given set, and that's the closure of your set. So now we do it likewise, hence this notation resembling the notation of a closure, but I'm going to argue that there is no topology in general for which the saturation operation is the same as the closure operation. Okay, but before we do it, we have a number of properties which hold for saturation. So that actually this concept holds water.
Piotr?
Yes.
But I'm like, it's a complete lattice. I'm like the same as like, for example, if you take ideals, an arbitrary union of ideals, it's not an ideal. It admits like a suprema, right? It still admits suprema.
Well, I mean,
it's just not that the union itself is the closure operation.
Well, the thing is that the union of saturated, even of two saturated subsets, the union of two saturated subsets is not necessarily saturated. So what I'm going to prove is the intersection.
The same for ideals, right? The union of two ideals is not an ideal.
Yeah. Well, it depends.
Or the union of anything else.
Theoretical union, yes, surely. But why would you say theoretical union? You just take the sum.
So, yeah, because I mean, like that's just like an analog of the statement. I'm just like comparing the analog statement.
It's a very poor analog because it's just this is, you know, when you take the union of ideals, well, it's kind of obvious that it doesn't have to be.
Okay, then take the arbitrary union of ideals. Take the arbitrary direct sum of ideals. You still have to close off, right? I mean, like the linear span.
Yeah. Yeah, maybe you're right. Okay, maybe this is an analog, yes. That the union...
I mean, like there are lots and lots and lots and lots and lots of examples like of closure operations that have this.
But look, let me turn it around into something interesting. Namely, the saturation property is really related to the ideals, because when you go to now graph sister algebras or Leavitt path algebras, then vertices label projections, or in Leavitt these are just idempotents, okay? And so when you take an ideal generated by these idempotents, and this is very important, there are some structural theorems about ideals which are kernels of morphisms and so on and so forth. This is extremely important in proving basic theorems. And look, if you have an ideal generated by projections labeled by some unsaturated set, then what happens is that all projections labeled by elements of the saturation of the set are in this ideal. Okay, so automatically, if you insert projections labeled by an arbitrary set into your ideal, and then you ask, okay, so what's the whole ideal? What kind of vertex projections it has inside? Well, then the answer is it has all vertex projections that are labeled by elements of the saturation of the set. Yeah. So this somehow relates this example to this ideal story. Okay, so maybe you're right. Maybe this is a good point.
I mean, if you think about it, like if you want what you want to compare in the end about saturations, is like compare the saturated planetary sets with the close two-sided ideals in your graph algebra.
Yeah.
So and there you have the same issue. That's basically
but that's what I just said. Yes.
Yes.
Yeah, this is what I just said.
So there's not really an issue with saturations.
What do you mean by an issue? Again, I'm having a problem reading your point. I agree what you're saying, but I don't understand what message you want to carry across.
That taking the union is not the right thing to do.
Sure.
Taking the set theoretic union is not the right thing.
Nobody says that it is.
Yeah, so there is no issue.
Well, I mean, the only thing I'm trying to say is that, well, first I want to say things that are positive, like with ideals. It makes sense to take arbitrary intersection of ideals, and it will still give you an ideal. But I wanted to make it clear is that this operation of saturation, which really resembles a closure operation in topology, cannot be viewed as a closure operation for some topology. This is impossible. I was completely wrong about it. So that's the issue. That's the issue. It looks like the closure operation, but it's not the closure operation.
It can be. I mean, like it's just not. It's
no,
just
no, it
not
cannot be because
operation
if
for
it were the closure, then you would have
closure.
the property that the union of the finite union.
It's not. It's just not. It's just the wrong space that you're looking at. I mean, like it's not the space of. So I mean, like if you take the ideal lattice, or if you take the lattice of saturated hereditary subsets, this gives rise to, this is a complete lattice, and it gives rise to topology, right?
Surely, but you are throwing.
So the spectrum. I mean, like what the real topological space to look at in this case would be just like the spectrum of this complete lattice.
But you are throwing too many ingredients into your soup. And I'm trying to clear up some basic statement with minimal amount of assumptions. I'm not combining, you know, I'm not talking ideals yet. I'm not combining hereditary and saturation together, because when you have things in a bunch, when you can prove many things, for special situations, implications hold. In generality, they don't hold. All I'm saying is that in general, the saturation property is not closed under the set theoretical union. So in general, you cannot create any topology on your subset of vertices such that the saturation operation would be the closure. Because if you could do it, then you would have, by the certain proposition I'm going to prove, you would conclude that a finite union of saturated sets must be saturated, which is not true. So that's the issue, if you want. The issue is that the saturation cannot be, in general, the closure operation for a topology. That's the issue. In general, I repeat, in general. This is in contradistinction with the property being hereditary. Arbitrary graph, whatever you want. And not only the topology, it's the Alexandrov topology of your most beloved preorders.
So your statement should be more precise, like in the sense that, like, not for any topology, but for any topology on the set of vertices.
Say it again, what?
So it should be not, the statement should not read for any topology, but for any topology on the set of vertices.
Yeah, but I haven't written the statement yet. So you are correcting something which is not written. So that's exactly what I mean. And this is exactly where I'm going to write it.
Yes.
So I'm kind of making a preemptive strike. Okay, but now let's begin with good properties of the saturation. Okay, but let me first clean the blackboard. So see, the good properties are the following. The empty set is saturated. The whole set of all vertices is saturated, and an arbitrary intersection of saturated subsets is saturated. So it really looks like a topology. But the problem is that in general, the union of two saturated subsets is not necessarily saturated. And that's why it's really something different than topology. And that's the issue. Okay, so first, observe that in any graph, we have both the empty set and the set of all vertices are saturated. Well, I guess it's obvious, because if you take the empty set, but nothing ends in the empty set, so the implication is satisfied. And when you take the whole space, then there is no regular vertex outside of the whole space. Okay, so this is why you have these two sets saturated, and the latter, namely the fact that E0 is saturated, the latter implies that the saturation always exists. Because in principle, you can ask yourself a question, what if there is no saturated subset containing a given set? But there always is, because any subset is a subset of E0 by construction. So the saturation always exists. Okay. But better still, you can prove the following proposition. So let E be an arbitrary graph, and Hi with I running over capital I be an arbitrary family of saturated subsets. Then the intersection set is saturated. This is precisely what you would have for closed subsets. And in particular, yeah, no, that's it. That's all I want. In particular, is in the next claim. Well, let's prove it. It's a short and elementary proof, but let's do it. So again, let's suppose that this is not the case. Suppose that the intersection is not saturated. In other words, suppose that there is a regular vertex, and you see this is very handy now to write just a regular instead of writing all these conditions. If there is a regular vertex V, which is not in the intersection set, and which has the property that everything that it emits ends in the intersection set. Okay, so this is exactly saying that the intersection set is not saturated. But then there exists J in I such that, well, if V is not in the intersection, then there exists a J such that V is not in AJ, okay? V is not in AJ. Well, and we still have that all edges emitted from V and inside the intersection set, but obviously the intersection set is contained in all of its components, in particular in Hj. So Hj is not saturated. Here it's very important to note that when I talk about the regular vertex, all I need to know is my graph. So once I know my graph, the regularity is fixed. So something doesn't change. So because later on we will define breaking vertices. And a breaking vertex is a breaking vertex with respect to a subset of a set of vertices. So a given vertex can be a breaking vertex for one subset, but not a breaking vertex for another subset. It's not an absolute concept once you have just a graph given, okay? It's a relative concept. But the concept of regularity is absolute in the sense that whenever you already have your graph fixed, then your vertex either is or is not regular. That's it, okay? So this is why when I pass to another subset, so first I consider the intersection subset, then I consider Hj, and it's still V is regular for both of them because V is simply regular in E, okay? All right, so this, I think, ended, right? Yeah. Yeah. So this is the desired contradiction, or if you want, we proved that if the intersection is not saturated, then not all of the components are saturated. So if all of the components are saturated, then the intersection is saturated. Okay. So let me not write anything any further. This is done. And this is a very nice property, which has some corollaries, which I'm going to write down. So see, Alex, a priori you could expect, well, if it behaves so well with intersection, maybe it behaves well with respect to the union. But you are right when you remember that this is very much related to ideals, then this is actually a good remark that it behaves similarly. Okay, so what's my corollary of this proposition? The saturation H bar of H, any subset, is the smallest saturated subset containing H. Right, and this requires no proof. I mean, this is really immediate, because if I have any saturated subset containing H, then of course the saturation is contained in this subset. So this is really the smallest, and it is saturated because of the proposition we just proved. So we know that H bar is saturated. This is what we just proved, okay? Because we proved that an intersection of arbitrary family of saturated subsets is saturated. This is defined as a certain intersection, which can be infinite, but it's an intersection saturated set. So this is saturated. And if you have anything else which is saturated, it contains H, then of course it also contains H bar. So H bar is really the smallest saturated subset containing H. There's no need to write it down, it's obvious. And so in particular comes here, right? So in particular, H is saturated if and only if it is equal to its saturation, right? And again, I suppose this is obvious because, well, if H is saturated, then the smallest set which is saturated containing H is obviously H itself, okay? And because H bar is the smallest one, then H is equal to H bar. On the contrary, when H is equal to H bar, because H bar is saturated by what is written before, then H is saturated. So we have an if and only if. This is implied by the statement above. Okay. And also we can conclude that immediately we can conclude that if you take the saturation property twice, this is equal just to the saturation. Right? Again, by the sheer fact that H bar is already saturated, so the small and the saturation of a saturated subset is identity. So H double bar is equal to H bar. Okay. So you see, until now, it really behaves. The saturation property really behaves like the closure property, and this is what fooled me. And I had hoped, well, maybe there is some topology for which it is a closure. Of course, it was complete nonsense. by the argument which I already gave you and discussed with Alex. Okay, but this is worth writing it down. So now, Alex, now is the statement for which you made a preemptive strike. So, however, in general, I repeat, in general, if you take an empty graph or something silly, then of course everything will hold. But in general, there is no topology on E0, just as you wanted, Alex. And this is how it's written in my notes, whose closure operation coincides with saturation. Oh my goodness. But yes, sorry, I'm writing it down. And because again, in general, that's important subclause, because in general, the union of two saturated subsets need not be saturated. Okay, and as an exercise, I want you to find a counterexample. So this is, I think, an exercise number 4.2 or something, I don't remember. Okay. Alex, are you happy with this formulation now?
Yes, very nice.
Okay, good, good. And I think we are done with hereditary and saturated. Now we can go to the breaking vertices. So now infinities will be coming into the game. No questions, I presume, about hereditary saturation. Okay. So the third property I want to unravel today is the property of an unbroken subset. And here I have to make a certain disclaimer. All that stuff about hereditary and saturated is in all textbooks. It's just everywhere. It's all over the place, okay? Although it's not often, I mean, at least I haven't come across it, discussed in terms of Alexandrov topology and stuff like this, although it should be, but I just didn't come across it. But things like hereditary and saturated are discussed at length in zillions of works in the literature, okay? Now, the definition I'm going to give you, I really have not seen it anywhere, and I think it's very handy, it's very logical. It follows sort of the mainstream of development. People just define breaking vertices, but for me, it's very important to define an unbroken set. Okay, and just as you define a saturated set as a set which does not admit a regular vertex outside of it which has some properties, the same with a unbroken subset. Subset is unbroken if it does not exist a certain infinite emitter outside of it which has some properties. And if I want to study admissibility issues of subgraphs, so that then my inclusion of subgraph into a graph induces a surjection at the level of Leavitt path algebras or graph-sister algebras, I need actually three properties. I need them to be hereditary, saturated, and unbroken. The set of vertices that I'm removing together with all edges that end at these vertices. So we introduced this term, unbroken set, but it might be called something else in the literature. I don't know. The only thing people agree about is breaking vertex, but we defined also this unbroken subset to be consistent with what you do in the case of hereditary or saturation property. Okay, so now let's write it. How are we doing in time? Not too bad. Today I have lots and lots of examples to show when we are done with this definition of general statements. So let E be a graph. A subset H of E0 is called unbroken whenever there does not exist maybe I'll write it like this. There does not exist a vertex V outside of it, and this is called a breaking vertex. And that's standard in the literature, such that it emits infinitely many edges and but if you look at the set or the subset of all edges emitted from V that have the property that they end outside of H, okay, that this set is non-empty and finite. So maybe you need a second to have this definition sink in. The vertex is a breaking vertex if we have the following situation. I have my subset H, this is E0. So well, if you want, the set is broken if there exists a breaking vertex V, and the breaking vertex V is a vertex which is outside of H, which is an infinite emitter, and it emits infinitely many edges into H and non-zero finitely many edges outside of H. So this is a breaking vertex, okay? And for those of you who are already fluent with Leavitt path algebras or graph sister algebras, you can immediately see why we care about it. Because when you go to a subgraph by removing all vertices in H and removing all edges that end in H, then in the subgraph we introduce additional relation, because what happens is that we change an infinite emitter into a regular vertex, and for regular vertex you have conscriptor relations. So introducing additional relations, so this doesn't hold water. You have a problem when you want to say, I create a subgraph by removing a set which is nice, hereditary, saturated, but it's broken. And when I define my subgraph by removing this broken subset, then I do not have an induced morphism at the level of graph algebras, okay? This is why this is important, and you can see it because you see, when you are in the big graph E, then V is an infinite emitter, so there are no conscriptor relations for an infinite emitter. But now when you go to a subgraph, in the subgraph, V becomes a regular vertex, and for a regular vertex, you do have conscriptor relations, which were not there before. Okay, so that's the issue. This is why we have to care about it. And such a maybe weird definition. I mean, from the point of view of graphs, this is very weird. I mean, why on earth would you care about such distinctions? Why does it matter? Okay, and of course, when your graph is, one of the things you can see immediately, when your graph is row finite, then all subsets are unbroken because you don't have infinite emitters at all. Okay. So this, I have it here written down, but I'm not going to write it on the blackboard. I just said it and let me repeat it, that if I have a breaking vertex of H, it becomes a regular vertex in a subgraph in which you remove H from the set of vertices and you remove all edges ending in H. Then you have a subgraph in which V is a regular vertex. It's not the sink and it's a finite limit. Okay, good. We are halfway through the notes. Okay, so we should manage by 2:15 at the latest. Now examples, examples, and one more time examples. I have 8 examples to give you. These are like candies for children, right? So do you have any question breaking the silence? No, the silence remains unbroken. None of you wants to be a breaking vertex for the silence. Okay. Examples. So I sort of waited with examples till I have all 3 properties together because it's more efficient. I'm writing a graph, I'm looking at subsets of the set of vertices, and then I'm deciding hereditary, saturated, unbroken, both, whatever, one but not the other, and it would be quite inconvenient to draw these graphs so many times. So this is why I waited for gathering together these 3 concepts in general and proving all elementary statements about them that came to my mind. And now let's really rock and roll with examples to see what we are talking about. So first, let's take my favorite Teplitz graph. So I have one loop and one outgoing edge. Let me label this loopy vertex V and the outgoing vertex W, okay? So what can we say here? That here, the one element set W is hereditary. Well, it is obvious because W is a sink. So it does not emit any edge, in particular does not emit an edge which goes outside. Okay, so W is obviously hereditary. But V is not hereditary. Precisely because there is an edge going from V to W. Okay. But all subsets of E naught, so this is my graph E, but all subsets of E naught are saturated. Well, we have only 4 subsets. The empty set and the whole set is obviously saturated. And now why is W saturated? Well, W is saturated because even though V is outside of this set and it emits an edge into this set and it's a regular vertex, well, it also emits an edge which doesn't end in W. So this condition, well, the saturation property is erased, the condition that all edges emitted at V and in W is not satisfied. So W is saturated, and when it comes to V, it's completely safe because the only outside vertex is a sink. So we are done, okay? And in particular, and of course, all subsets is unbroken because it's a row finite set, a row finite graph. So if you want to have all 3 properties together, so it's hereditary, saturated, and unbroken, then you can take W, okay? This set is hereditary, saturated, and unbroken. So this means that you can delete this vertex and an edge that ends in this vertex, and you'll have a nice graph algebra homomorphism. This is the famous symbol map from the Teplitz algebra into the circle algebra. But you cannot do the other way around. You cannot kill this vertex. Okay, so this was my Teplitz example. Next, 2x2 matrices. So I take now E to be the graph consisting of 2 vertices V and W and just one edge in between them. Okay, so what happens here? if I look at W, then this is hereditary, but not saturated. Well, W is hereditary because it's a sink, so it does not emit anything. And it is not saturated because there is a vertex outside of the set, which is a regular vertex and emits all the edges into this set. So it says, well, it would be nice to have a name, right? If I have a vertex which witnesses the failure of the subset to be unbroken, so a vertex which breaks the set, breaking vertex, how should we call a vertex which witnesses the failure of a subset to be saturated? I don't know, unsaturating vertex? Here are certain inconsistencies that when it comes to hereditary and saturation properties, you just give names to subsets, but not to vertices. And now when you go to this unbroken stuff, then you give a name to a vertex, but not to the subset. Perhaps we should have names for all two things in all three cases. Okay, so this is W subset. Next. And maybe it's worth noting that the saturation of W set is the whole E0, so VW. Yeah, that's clear because W is not saturated, and the only set in which the W subsets contained is the set of all vertices. Okay, so you see the saturation always exists. This is exactly what we just did. And now when I look at, so let me look at this subgraph. So I define the graph F as follows. I remove W from the set of vertices. From the set of edges, I remove all edges that end at W. And then I restrict the source and the target maps. And when you look into this particular situation, what you will get here will be just one element set W. The set of edges will be the empty set. And then, of course, restrictions exist to an empty set, right? So I have S empty and T empty. These are the empty maps if you want. Okay, so indeed it's a subgraph because I said as the source and the target maps restrict. They are just trivial maps, the empty maps. They are defined on the set of edges which is empty, so everything holds what you want. So this is a genuine subgraph, and I can write is a subgraph of E, but swapping the roles of V and W would not yield a subgraph. And I guess what I missed here is that, I should one more sentence be written here, namely, I removed W. Now, when I remove V, well, you see, the thing is that it wouldn't work because the set consisting of one element V that set is not hereditary. And we proved the proposition that when you construct the subgraph precisely in this way, by removing a subset of vertices and appropriate edges, and that set of vertices is not hereditary, then there is no subgraph. The restriction does not exist. In other words, what happens is that your set of vertices in your subgraph, you apply the source and the target map, and one of them, I don't remember which one, does not land in the designated set subset of vertices. Okay. So this is the case of 2 by 2 matrices, if you want. Okay. But you see, having a subgraph is not enough. This is true that I can have a trivial subgraph which is just consisting of one point. Okay, so it's true that V is a subgraph of E. All right, but it's not good enough because it's not saturated, and there is no morphism. There's no morphism from the algebra of 2 by 2 matrices to complex numbers, because 2 by 2 matrices is simple algebra. There's no ideal. Okay, so you need to really have a morphism at the level of graph algebras. You really have to have both properties at the same time, hereditary and saturation. And indeed, in the literature, they are often spoken about in one go. Very, very frequently, one sees the phrase hereditary saturated. For some time, I thought that you cannot define one without the other, but these are, of course, two completely different independent definitions. Okay, so these are 2 by 2 matrices. Now, let's introduce some infinities. But actually, before we do this, let me mention the following examples for unbroken sets. So all subsets of E naught are unbroken if E is row finite. I already mentioned it, but it's worth writing it down so that it does not escape your mind. Okay. And in any graph, not necessarily row finite, both the empty set and the whole set are unbroken. Well, this is obvious, because if your H is the empty set, then you cannot have infinitely many edges ending there because nothing ends there. And if your set H is the whole set, then there is no infinite emitter outside of the set. Okay, so this is trivially satisfied. So as we can conclude right now, the empty set and the whole set for any graph is always hereditary, saturated, and unbroken. But this just means that if I have the empty set as a subgraph in any graph, then I take my graph sister algebra or Leavitt path algebra of the graph E. And here, if I get the sister algebra of the empty graph, this will be the zero sister algebra of, if you want, all continuous complex valued functions on the empty set. And of course, the zero morphism always exists. Sorry, I'm doing it. Sorry, I'm doing something stupid, I guess. Wait. So this is a subgraph. So I'm removing. No. wait a second. This is not what I wanted to do. Yikes. So H is equal to the empty set. When H is equal to the empty set, then my subgraph F is just equal to E. Okay. And the map that we are talking about is the identity map. So this always exists. Okay. Right, because then I remove from E0 the empty set, so everything stays as it is, and from E1 I also remove the empty set. So we have this equality, so if there's the identity map. And in the second case, when H is equal to E0, then F is the empty graph. And F is the empty graph. So now we are talking about the map from C star of E to C star of the empty graph, which is the zero C star algebra. So the identity map and the zero map always exist. Okay, so this should be no surprise. Okay, now let's take the Polish quantum sphere, or if you want the minimal integration of compact operators, or if you want to be in the realm of Levitt-Path algebras, let's take the minimal integration of the algebra of all finite matrices, which is a non-unital algebra. So I take our graph E to be as follows. We have two vertices, V and W, and we have countably infinitely many edges going from V to W. Okay? So if I look at W, then it's both saturated and hereditary. You see, the hereditary property is the same as in the case of matrices. It's simply a sink, so it cannot spoil the hereditary property. But V is no longer a regular vertex. It is an infinite emitter. So the fact that it emits all its edges into W is irrelevant. Okay. And indeed, what happens is that you can kill the vertex W. And indeed, you have a star homomorphism into complex numbers from the minimal unitization of compact operators. And you don't have any map from 2x2 matrices into complex numbers. Okay. And also let me remark, so W is both saturated and hereditary, and V is saturated but not hereditary. And V, when I say VW, I mean one element set containing VW, is saturated but not hereditary. Yeah. Well, V is saturated because outside of V there is only a sink, so we are done. And it's not hereditary, well, because it emits something which goes outside of a set, all right? So we don't have any morphism when we remove, we can remove W, but we cannot remove V, okay? I mean, we wouldn't even have a subgraph because it's not hereditary. And maybe it's also worth remarking that all subsets are unbroken. So this graph is no longer row finite, okay? You can have it the other way around. So you can have a vertex at which you have infinitely many edges ending, but row finiteness means that there's no vertex which has infinitely many edges emitted from it. So here all subsets are unbroken. We'll have just 4 subsets. 2 are obvious, and when I look at W, why is it unbroken? Because when I look at W, the only vertex outside of it is V, but V does not emit anything outside of W. Okay, so it's not a breaking vertex. So V is good. Now, when you look the other way around, it's also good because W is a sink, so it does not emit anything. Okay, so all subsets are unbroken. So in particular, this guy is both hereditary, saturated, and unbroken. So indeed, we do have a map. We do have a map from C star of E to, well, C star of just one point graph, V, which is just the complex numbers. And this is, if you want, the minimal unitization of compact operators, or if you want the Podlesh quantum sphere. And if you remember, if you know the stuff about the Podlesh from quantum groups, then you know that it has one character, the North Pole, and that's exactly the character that we obtain here. Okay? So the North Pole in the Podlesh quantum sphere is exactly given by this vertex. Sorry, it's given by V, because V survives. Yeah. Anyway, that's this homomorphism. So classical point of a C-star algebra is a star homomorphism to complex numbers. So in fact, this map is a point. Okay, so this was number 4. Now, if you remember from your recitation classes, we were doing some projective spaces, weighted projective spaces, kissing spheres, right? We are gluing 2 spheres over 1 point. And, well, we can have the same construction in graphs. So this is my example number 5. I take my graph to be given by 3 edges. And in the middle edge is the only emitter. It emits infinitely, countably infinitely many edges from itself to the right and to the left. Okay? So this is, if you want, the quantum version of a weighted projective space, which you should remember from recitation classes. Okay, and in this graph, all subsets are unbroken. I don't want to bother about hereditary saturated. We've had enough about it in the case of row finite graphs. But let's handle these infinities. So here, all subsets are unbroken. So here we have 2 to the power 3. I have 8 cases to consider. 2 are obvious. I have actually 6 non-trivial cases. So I have 3 one-element subsets, and I have 3 two-element subsets. Okay. So first, let's look at these one-element subsets. So maybe I should label it somehow. V, W, W prime. Okay. So when I look at W prime, there are 2 vertices outside of the set. One is a sink, so it doesn't matter. The other one is an infinite emitter, so it potentially can be a breaking vertex, but it is not the breaking vertex because the amount of edges it emits outside of this, it emits that end outside of this one element set containing W prime is infinite. And in the definition of breaking vertex, it was very important that the number of edges it emits outside is finite, it's non-zero and finite. It's infinite, okay? So this is unbroken. But for the sake of symmetry, also the one element set containing W is unbroken. So how about V? Well, V is trivial because both vertices outside of the V subset are sinks. They do not emit anything, okay? So this is one element subsets. How about two element subsets? Well, when I take W prime and V together, then I'm done because the only vertex outside is a sink. For symmetry reasons, the same happens when I take V and W together. So what when I take W and W prime together? Well, then V is an infinite emitter, but it emits all its edges into the subset W prime, okay? So there is nothing emitted outside. So you see, when the number of edges which is emitted outside is infinite or 0, it's fine, it's not a breaking vertex. The problem is when you have finitely many which are emitted outside, because then they introduce conspiracy relations. So we have to be careful with this, okay? So this is weighted projective space. Now, let me consider, maybe I'll still squeeze it in here. Example number 6. I'm going to do something very similar. This is like gluing a Podlesh quantum sphere and 2 by 2 or n by n matrices, I suppose. Okay, so from V to W, I have countably infinitely many edges, but from V to W prime, I have finitely many edges. Okay, so this is my graph E. And what happens here? So I think I drew such a picture at the very beginning when defining a breaking vertex. This is like a canonical example of a broken set. So here, the set W is broken, and V is its breaking vertex. Okay, that's just by very definition. This is an infinite emitter outside of the set, and it emits finitely many non-zero edges outside of the set. That's it, it's a breaking vertex. So the subset W is broken. Okay, and now the examples 7 and 8 are exercises 4.2 and 4.3. I want somebody to do these exercises in a week. So first, construct a graph with 2 unbroken subsets whose union is broken. So this is what we already discussed. That there is. Sorry. So there are actually 3, 3 exercises. One was also with this union of saturated. Sorry. So I should have. There should be one more thing, and I forgot to write it down in the exercises. Darn. Yeah. I should have 3 more problems, not 2. Anyway, so you see, when it comes to unbroken sets, they are not good with respect to the union nor the intersection. These are different examples, but you can write down very simple graphs which have the property that they admit 2 unbroken subsets whose union is broken, and then you can stack another graph with another pair of unbroken subsets whose intersection is broken. So your task for the exercise is to construct such graphs and such pairs of unbroken subsets. Okay. And one more exercise, I'm going to call it, I don't know, 4.3, is about an example. I also want somebody to construct an example of a graph with a pair of saturated subsets such that their union is not saturated. Okay, so this is what I leave for exercises because it's elementary, but it's cute. You have to. It just shows that you understand what the definition is. So I think it's worth it that you do it yourself. Although, to be honest, the plain truth why I didn't do it myself is because drawing these graphs takes way too much time. So yeah, I couldn't type it because it would take me forever to type these graphs which I cooked up. They're simple, but still, I mean, doing it in LaTeX is complicated. So I sort of dumped it on you. Okay, so these are my examples. If you want, you can count 9. 6 are explicit, 3 are for you to do. And what remains are 3 elementary remarks which concern how do these properties of being saturated, hereditary, and broken behave when you restrict your graphs or when you extend your graphs. You see, we already mentioned it a week ago, I believe. Like in topology, right? Some concepts are relative, some concepts are absolute. If you consider, I don't know, the unit interval, in the unit interval, it's of course open. But when you consider it in real line, it's not open, right? So, so the property of being open is relative, okay? You have to say what's your ambient topological spaces. If you consider it in a larger, bigger topological space, it might fail to be open. Of course, I'm all the time talking about the induced topology. But when you consider the property of being compact, if you have a subset that is compact in some topological space, it is compact in any topological space which is larger, and it is compact in any topological space which is restricted, which is a smaller but still contains the subset. So compactness is absolute, but not say openness. Okay. So now I'm asking these questions about unbroken, saturated, and hereditary subsets. What happens if something is unbroken, hereditary, or saturated in a graph? What happens when I extend the graph? And what happens when I restrict the graph? How do these properties behave? And that's the last thing I want to do today. Yeah, I think I can start erasing here. So elementary remarks. First, the properties of being hereditary and saturated are not preserved by extensions of graphs. I mean, in general. So A, if I look at the 2 by 2 matrices graph DW1 edge between V and W and edge E, I look at it as a subgraph in a 3 by 3 matrix graph. So I have V, W, W prime, and I have edges E and D prime. E goes from V to W, and D prime goes from W to W prime. Okay. So this is a subgraph, all right, because I do have. I'm not changing the. Sorry, no. I'm removing W prime, and I'm removing all edges ending in W prime. W prime is a hereditary subset in this graph, so removing it and all edges ending here gives me a subgraph. So this is indeed a subgraph. And well, if I look at W, so W is here, so let's call it F, and let's call it G. Okay, so the subset W, which is in both graphs, this is hereditary in F, but not in G. Is hereditary in F, but not in G. So throwing this one more edge and one more vertex spoils the hereditary property of W, which is obvious because W used to be a sink, but it ceased to be a sink once we added an edge which is emitted from W. Okay, so you see, hereditary property is not preserved by, in general, by an extension of graphs. Now, let's do something similar. The only thing I'm looking here, and I think this is exactly the same situation of F in G. I'm looking if arrows are reversed. No, but they go the same way. Okay, so the graphs are as before. So now I claim that V is saturated in F, but not in G. So all I changed was my subset, right? Now I take the subset V, and of course it's saturated in F because, yes. Okay, sorry. I now I understand why I did the the picture twice. You see, the thing is that now I add this additional edge from the other side. So sorry, I have to draw it. The graphs are the same, but the inclusion is different. Okay, so now I have the same, V, W, E, but this is included, and now I have this VW on the right, and I add my E prime vertex on the left. Okay, so it's a different inclusion. So this is included as the first part, and this is included as the second part. Okay, and now I look at the first vertex, not at the second vertex. And now that's my inclusion F and G, and I can write that V is saturated in F, but not in G. Right, this is obvious. In F it is saturated because the only vertex outside is a sink. But this is no longer the case here because I have a vertex W prime, which wasn't there before. It is outside of my set V, and it's a regular vertex, and all its edges end in V. So this is an unsaturating vertex. Okay, so V is saturated in F, but not in G. So you see, extension ruins the property. Okay, this was, but you see, this was in general. This was in general. Now we can consider a special case when things are better behaved. So this is a very important statement, in fact, for what we're going to prove later on. However, both properties are preserved by the special extension. Both properties are preserved by the extension F, a subgraph in F union G. And for which set? And it's not for any set. And so for the special, for the extensions of that form, okay, for the set H equal to F naught less the intersection of F naught with G naught. So, okay, I assume that the intersection graph exists. So in other words, the source and the target map exist on the intersection of F1 and Fg. They agree on the intersection of F1 and G1. And then the union graph exists. And then I know that F is a subgraph of the union graph. We discussed it already. So this is a very special type of an extension. And now I'm looking for the special type of a set. Namely, I take the set of vertices in F with all vertices in G removed. Okay, so this is my subset H, and I claim that here the saturation and hereditary property is preserved by this extension. So if this H is saturated and hereditary in F, it is saturated and hereditary in F union G. Okay, and this is because there are no edges like this. I have my F, I have my G, so F and G, and this is if this is the union graph, then you do not have an edge which starts in F but beyond G, and ends in G but beyond F. Okay, such an edge does not exist because, well, since its beginning is in F, it means this edge must belong to F and into F1, and now its end is in G. Well, the thing is, okay, that edge must be either in F1 or in G1. Call it E, right? So E is in F1 union G1. But if E is in F1, then both its beginning and its end must be in F. But this is not the case because the end is not in F. If this is in G1, we again have a problem because now the beginning is not in G, okay? So there is not an edge like this in the union graph. Now this is important. And now we can prove that this hereditary and saturation property is preserved. So let's have a look. Assume that H is hereditary in F. So what does it mean? It means, so this is my H, okay? So everything in F, which is outside, well, maybe I should write F naught, G naught. Everything in F naught, which is outside of G naught. Well, it is hereditary in F, so this means that there are no edges starting in H which go to this intersection, right? There are no such edges. But since there are also no such edges, this is also hereditary in the union, okay? Now, let's consider this saturated. Okay, so assume that H is not saturated in the union, okay? H is not saturated in the union. So this means that there exists a vertex which is outside of H. And there are two cases, I suppose. I can have this vertex here or in there, okay? And it is a regular vertex. Yeah, the thing is that it is a regular vertex. It is a regular vertex in the union, okay? So it emits finitely non-zero and finitely many edges which come either from F1 or G1, okay? And if all of them, and so we have two sets of edges. We have edges from F1, we have edges from G1. When I have an edge from G1, it cannot end here. So if it emits any edges from G1, then it cannot be unsaturating vertex for the set because edges from G1 cannot end outside of G. Okay, they cannot end in F naught, which is not in G naught. So this we can forget. So what if it emits edges. Aha, and I cannot consider such a vertex because there are no edges like this, okay? So in fact, I only consider vertices which are in the intersection, and then I cannot consider edges from G1, so I have only edges from F1, okay? So I have a regular vertex which emits finitely many edges. They are all edges from F1, and they all end in H. But then this is an unsaturating vertex in the graph F, because everything is in F. Okay. So this implies H hereditary H in F naught union G naught. Hereditary H in F naught union G naught saturated. So you see, for the special case it holds, but the key thing is that there are no edges which span from outside of F into F and from outside of G into G. Okay, so this was my first elementary remark. Now the second one. The restrictions of graphs to subgraphs need not preserve the saturation property even in the special case. So restrictions of graphs to subgraphs need not preserve the saturation property even in the special case. Of restricting F union G to, so maybe actually like this, F union G restricted to F, and H being defined as before, F naught minus G naught. Okay, indeed, let's give a counterexample. So saturation is more nasty, I would say, than the property of being hereditary. And perhaps because it's a purely graph theoretical concept, you don't need any algebras to talk about to understand it. It gives you everything. It gives you Alexander's topology for the natural preorder. It's closed under elementary operations for arbitrary families. At least for the special case, it behaves well under restriction or extension. Sorry, extension. Okay, so let's see this counterexample. I write the following union of graphs. Maybe I'll write it up here. I write F union G as, okay, so I'm just putting together 2 by 2 matrices. I have one edge, call it G1, going from V to W1. That's my first graph, F. Now my graph G is an edge G2 going from the same vertex V to a new vertex W2. So of course the intersection graph exists. This is a graph with the empty set of edges and one vertex V. And since the set of edges is empty, of course the source and target maps agree. So this union graph exists, it's well defined. And now, of course, when I write it down of what it is, this is the following graph with 2 edges and 3 vertices. And now when I look at H, so H is equal to 1 element set containing W1, right? Because I remove from the set W1 comma V, I remove V, okay? So H is just 1 element set containing W1. And this is saturated in the union set. In the union graph, sorry. Right, so W1, and why is it saturated? Well, because when you look at the 2 outside vertices, W2 is a sink, so it doesn't matter, and V is a regular vertex, but it's not true that all edges it emits end in W1, okay, because there's another edge would end in W2. So it is clearly saturated in the union, but it is not saturated in F. Right, because now V is a regular vertex in F, and all the edges it emits end in W1. So this is an unsaturated vertex for the W1 set, okay? So here, even the restriction from, in the special case, the restriction from the union graph to a subgraph, one of the component subgraphs, with this particular H being equal to all vertices in the subgraph which are not in the other component graph, even then it doesn't work, okay? But with hereditary property, it works. So this is the negative statement, and the positive statement is the following. However, the restrictions of graphs to subgraphs So the first remark was about extensions, right? And what we saw is that in general, extensions do not work at all. They spoil both properties. Now, when we look at the second remark was when we look at restrictions of graphs to subgraphs. Wait, and where it was? Sorry. So even in the first remark, both properties are preserved. Yes, exactly. So the case of extensions can be saved when we consider a very special case. All right. So in general, nothing works. In the special case, everything works. Now, how about when it comes to these two properties? Now, how about restrictions? Okay. So when it comes to saturations, it's hopeless because even in the special case, the restrictions do not work. This is what I just proved to you. And now the question is, what happens when you do the restrictions for the hereditary subsets? Okay. So this is the discussion right now. So the restrictions of graphs to subgraphs always preserve the property of being hereditary. So you don't even need a special case. Right, so this is a big contradistinction with the saturation. So the saturation, the restriction of saturation subsets, the saturation property fails even for special restrictions, whereas the hereditary property holds for arbitrary restrictions. Okay, and okay, So which means what? That if I take H a subset of F naught and F a subgraph of G, okay? And if it's not hereditary in F, it's not hereditary in G. So in other words, if it is hereditary in G, then it is hereditary in F. So restriction works. And how do we prove it? If there is a path in F starting at V in H, and ending outside of H, and ending at W not in H. So this is just saying that F is not hereditary, right? Yeah, because it's a path is in F. Then it is also a path in G. Sorry, yeah, a path in G, yes. Right, because F is a subgraph of G. So any path in a subgraph is a path in a bigger graph, because any edge in F is an edge in G, and then a vertex in F is a vertex in G. And moreover, remember that the source and the target maps are in agreement when you restrict to the subset of edges. So all these conditions defining a path that the source and the target of appropriate edges agree, they agree when whether you look at the restricted source and target maps or the full big graph source and target maps. So this is obvious that a path in F is in a path in G. And well, it has the same property, right? This is it's also a path in G, which starts in H and ends outside of H. So here I have G naught, that's H. Right, because you see here when I write W naught in H, well, I consider it, sorry, I should, this was sloppy, no. What I meant here, and this is what is written in my notes, that the W is in F naught less H, right? Because I'm assuming that H is not hereditary in F. So there is a vertex W outside of H, but inside of F naught, okay? But of course, since F naught is a subset of G naught, F naught minus H is a subset of G naught minus H. So if I have such a path that ends in W in this set, it ends in W in that subset. So now it is not hereditary in G. So the restriction works for trivial reasons, okay, for hereditary subsets. Right, I have one last elementary remark. And this is, so this was about hereditary and saturated, okay? This is the stuff I did a long time ago. But now I added one more remark about unbroken subsets. And I must say that I was too lazy to consider special cases. Maybe one should do it. By the way, the properties which we just discussed of a saturation, this is exactly what causes a problem that, you know, when the intersection subgraph is obtained by removing hereditary and saturated subsets, then you can say that also each of the graphs is obtained by removing hereditary saturated subsets from the union graph. So somehow, if you know what I'm driving at, if you have morphisms from graphs into, from the graph algebra of graphs into the graph algebra of intersection, of the intersection graph, when they induce morphisms going from the graph algebra of the union graph into the graph algebras of these particular component graphs, but not the other way around. And the obstacle is exactly here. Even in the special case, that saturation is delicate. I think that it is related. It came from somewhere. Okay, so now just about unbroken, okay? So the property being unbroken is just ruined by both extensions and restrictions, but I didn't consider special cases. So just let me do this. So as my remark number 3, the property, yeah, 3 minutes to finish, of being unbroken is neither preserved by restrictions nor by extensions. Right, so first I look of a restriction. So this is my big graph, call it G. And I have countably infinitely many edges from the first vertex to V, and countably infinitely many edges from V to the last vertex, W. And my subgraph here, F, is just obtained by keeping the same vertices, but now having only finitely many edges from the first vertex, the leftmost vertex, into V, and still the same number of countably infinitely many edges from V to W. So here I removed infinitely many edges, so that only finitely many remained, and here I removed nothing. And obviously F is a subgraph of G because I didn't fiddle with a set of vertices. The sets of vertices are the same, so of course all restrictions work. Okay? And you can see that when it comes here to we always look at the set W. Yeah, there's one element set W. Okay. So W is W. Oh, wait. I did the edges in the wrong. So this is like in this weighted projective space. Sorry, this is important that they map in the opposite directions. Okay. So when I look at W is unbroken in G. In G, broken in F. Right, this is obvious because in G, this vertex is a sink, and yes, this is an infinite emitter, but it emits infinitely many edges outside of W. Done. It's not the breaking vertex. But here, this is exactly the canonical example which I gave you of when a vertex is a breaking vertex. So this set here is broken. And now when I look at the extension, so now I'm taking as my F a graph which has a finite number of edges going to the left, a finite number of edges going to the right. So this is my F. And I include it in this guy. So I just rewrite it. Finite, countably infinite. Okay, so I'm not changing anything with pointing left edges. They remain the same. But I throw in additionally infinitely, countably infinitely many edges going from V to W. So this is my extension of F to G. Okay. And again, when I look at W, of course, W is unbroken in F because this is a row finite graph. So every subset is unbroken. And of course, like before, it's broken in here. So this ends my elementary remarks. And this is just the time to finish. I have one more, maybe non-elementary, more philosophical remark to make. I'm not going to write it down. It's written in the lecture notes. So you see, in mathematics, you have this property of being hereditary, right? So if a property of an object restricts to the property of any sub-objects, we call such a property hereditary property. Okay, so for instance, the property of being abelian is hereditary among groups. Because if you have an abelian group, any subgroup of an abelian group is abelian. So being abelian is a hereditary property. And in this sense, the property of being hereditary is hereditary among graphs having H as a subset in the set of vertices. So somehow terminology agrees, right? The property of being hereditary is a hereditary property in this meta-mathematical sense, right? And I think this is a good time to stop. I'm done with the material prepared for today. And for the final lecture of the semester, I want to prove a theorem about admissibility of subgraphs and strong admissibility of subgraphs. So this is already in the ballpark of pullbacks of Levi-Pav algebras and graph system algebras, and I want to end it with a nice theorem. But this is why today I had to finish this preparatory material. So it will be admissible and strongly admissible subgraphs, and push out, if you want, theorem next week to end the semester. For the time being, let me stop recording. I stop this lecture, and let's resume in 11 minutes, okay? 2:30, and we'll have 1 hour recitation class. Okay, stop recording. See you in 10 minutes.